This equation, ds squared equals dt squared plus dx squared, defines a standard Euclidean metric. It ensures spatial distance is measured equally, drawing a perfect circle. To describe our universe, we change one operator. A plus becomes a minus. This Minkowski line element contorts our circle. By redefining how we measure separation, we map the geometry of causal possibility from first principles. In Lorentzian space, the metric acts as a local constraint, defining which events possess physical influence. We must view the universe as a collection of events, coordinates mapped in both space and time, rather than static points in a void. Between any two events, determining causal precedence is the priority. The critical question is whether a physical signal from one event can reach the other. The minus sign creates a Lorentzian signature, forcing every displacement into a category of physical permission. This architecture organizes space and time into a directed hierarchy. Movement occurs only along permitted pathways, overriding our intuition of equal distance in every direction. To understand spacetime, we must adopt a relational, causal perspective and abandon standard Euclidean logic. We can observe this by plotting an event at the origin of a two-dimensional Minkowski grid. These three vectors represent different types of displacements extending into spacetime. Under the minus-plus sign convention, any vector where the interval ds squared is less than 0 is a timelike displacement. Timelike paths represent physically possible trajectories. These are the routes available to massive observers and material clocks. If the calculation shows that ds squared is exactly 0, we have a null or light-like displacement. Null paths represent the absolute limit of propagation. These are the trajectories of massless signals like photons. When the interval ds squared is greater than 0, we call it a spacelike displacement. Spacelike paths cannot be traversed by any causal signal. They are physically disconnected from the origin. These three classifications are invariant laws of nature. They govern the exact boundaries of where any particle or signal can physically go. This distinguishes the chronological future, the open set of time-like reachable events, from the causal future, which includes the hard null boundary. If we sweep our gold null vectors outward symmetrically from the origin, they trace the limits of future and past influence, forming these V-shaped light cones. The interior of these cones contains every time-like path an object could take from this event. Building a functional causal geometry requires a second, causally connected event to define a region. If a second event Q occurs within the future cone of our original event P, a new past cone projects downward from Q. The mathematical intersection of these two regions creates a distinct geometric structure, the causal diamond. This diamond represents the finite, local domain of possible interaction between two events. It is the fundamental unit of a causal universe. It is tempting to measure the height of this diagram to determine physical distance or elapsed time. This is a visual trap. The chain between two events on a screen does not map directly to physical proper time. If we apply a coordinate shear to the grid, the diamond skews and the drawn ruler shatters. The apparent lengths and pixel counts change completely during this distortion, yet the causal architecture remains mathematically untouched. The arrows, null boundaries, and path classifications maintain their geometric integrity. We cannot equate pixel height to proper time without adding models, scaling, and sampling assumptions. Lorentzian invariant geometry survives coordinate distortion, while the apparent screen geometry fails. A well-behaved local light cone is not enough to ensure a stable universe. Local cones can curve around a manifold and intersect their own past. To ensure predictable physics, we must scale up to a global condition called global hyperbolicity. We reach it by climbing the causal ladder. At the base of the ladder, chronology forbids closed timelike curves, and causality forbids closed null loops. Strong and stable causality sit higher on the ladder, ensuring that causality remains intact, even if we widen the light cones or perturb the metric. The highest rung is global hyperbolicity. Here, causal diamonds are strictly compact, providing the architecture required for deterministic evolution. These levels are distinct topological constraints, each eliminating a different causal pathology. Predictable evolution is a property of global topological architecture, not just the isolated rules of a local light cone. If we treat entire extended regions, rather than point events, as the unit of space, our mathematics shifts. In this shift, a full causal diamond ceases to be an area. It becomes a single coordinate in a higher geometry. This is kinematic space. In advanced physics, kinematic space is an auxiliary geometry where individual points represent entire causal diamonds. This allows physicists to encode complex bulk geometry and entanglement through the relationships of boundary regions. Boundary intervals on this theoretical cylinder map to extremal surfaces that slice through the interior bulk spacetime. These extremal surfaces are used in holographic entropy prescriptions to measure quantum entanglement. These mappings require specific hypotheses and precise theoretical settings to function correctly. This interval construction cannot be generalized to every space of relations without new mathematical evidence. We must distinguish clearly between local cone rules, finite diamond regions, and global holographic frameworks. Altering one mathematical sign establishes a hierarchy of causal structures, replacing Euclidean visual intuition with the geometry of possible influence.